So I need to share the screen.
Where are the video recordings being stored for these for the seminar? I didn't. Are they on the website? I looked around.
No, there's a playlist on YouTube for New York Number Theory seminar.
Okay, it's on YouTube. Thanks.
I had to ask Mel where mine was because I looked for it for 3 days and couldn't find it. You should send me the link so I can put it on the web page.
I think if you search YouTube for NYNTS, then that will come up. That's part of the title of all of these.
Right. So let's see. Can you see my?
Yes.
Slide? Excellent. Okay. So let me explain what's going on. As I mentioned last week, there was some remarkable work by two separate groups of mathematicians on an extremely interesting problem, which is if you have a polynomial and you in several variables and you look at its range, if there is some kind of bias in the distribution of values of the polynomial, does that tell you anything about the polynomial? For example, whether or not it's irreducible or to what extent it factors and so forth. So there's a Cuny connection to half of this because some of the work was done by Guy Moshkowitz, who's on the faculty at Baruch College of Cuny, and someone named Alex Cohen, who was in an REU at Cuny last summer and did this work with Moshkowitz. At the time, Alex was a graduate student, was an undergraduate at Yale, and now he's a graduate student at MIT. And they have a preprint on, two preprints on arXiv. Similar work was done by three people at Hebrew University, Dima Kajdan, Tammy Ziegler, and a third person whose name I can't pronounce. And I invited, and Moshkowitz is going to give a talk in this seminar in 3 weeks. So since I didn't have a speaker for today, I thought I would try to give some of the preliminaries that put what Moshkowitz might be talking about in some context. And so I'm still trying to understand a lot of this because I hadn't really looked at, even though some of this, the main result, which is about what are called cap sets, has been known for about 5 years. I had never really looked at it. And even though it uses, in the original proof, something called the polynomial method, which appeared for the first time in a paper of Alon Ruja and myself. So what I'm going to talk about is cap sets and what is called the slice rank of tensors. So, oops. How does this go? Cap sets, okay. Yeah, so, and this isn't a completely expository talk. It's based on a solution to what is called the cap set problem, which was done by Krutlev and Pach, and Ellenberg and someone whose name I also cannot pronounce, solving what is called the cap set problem in vector spaces over a field with 3 elements. And cap sets. So first of all, I have to say it's a terrible name, which conveys nothing, but it is what has become the standard name, and it's the following. So you have a finite subset of subadditive semigroup. So classically, the most interesting finite subset of an additive semigroup is a finite set of positive integers, or for example, you can take a finite set of vectors. And a 3-term arithmetic progression in the set S is a set with 3 elements, A plus B, A plus 2B, where B is different from 0. And a cap set is a subset of the set that contains no 3-term arithmetic progression. So the cap set problem, at least one form of it is given a set S, determine the sizes of the maximal cap sets. And in particular, calculate the size of, actually I should have said the smallest cap set in S. sorry, no, this is right. The largest cap set in S. That is,
Yeah.
how
When you
large
say
can a set
maximal,
be? Sorry?
when you say maximal, you mean that you can't add any elements to it. So the
Correct.
largest cap set is maximal, but not all the maximals are large.
Right, then you can have cap sets of different sizes. So in particular, we asked, what is the largest cap set? Oops. So a slightly easier problem, if you can't calculate the answer exactly, is to find upper and lower bounds for the size of the largest cap set in S. So if M is an upper bound for a cap set, that means every set with more than M elements must contain a 3-term arithmetic progression. And if L is the lower bound for a cap set, or a lower bound for a cap set, or the lower bound for a cap set, then there must exist a set A that's a cap set that contains at least L elements and no 3-term arithmetic progression. So I seem to be jumping around. Oops, I might have erased a few slides. Let's try.
What would you call cap sets if you had to name them? Just progression-free sets?
Sure. That's slightly better.
Three.
Better, yeah. I mean, just cap sets. I mean, Kevin can explain where cap set comes from. The idea is if you have, for example, a sphere and you slice it with a plane and that slice off what you call a cap, then any line through that cap can contain at most 2 points on the surface of the sphere. And I think there's some constructions of large cap sets that use this geometrical idea. And I think Kevin actually did some serious work on this a few years ago. So instead of looking at sets of integers, let F3 be the field with 3 elements. So F3 to the n is the vector space of dimension n over this field. And we can look for a cap set in F3 of n. So F3 of n contains exactly 3 to the n vectors. So an upper bound for the size of a cap set, of course, is 3 to the n. Because you can't have a cap set with more than that. But that's kind of stupid. And 25 years ago or so, Mashula proved that an upper bound for the size of a cap set is a little bit smaller than 3 to the n, is 3 to the n divided by n. And sometime after that, this was improved by Bateman and Katz, who proved that there's a positive number c, so that an upper bound for the size of a cap set is 3 to the n divided by this, still relatively small amount, n to the 1 plus c. So it's still, all these 2 non-trivial estimates are not exponentially smaller than the trivial bound of 3 to the n. And getting a number smaller than 3, an exponential, something to the n, where you're raising a number less than 3 to the power, that was like a famous problem for a long time until just a few years. Oh, sorry. And then there was a lower bound. In 2004, Adel constructed cap sets with more than this number of elements. So you can have reasonably large cap sets. And the big achievement of Krutlev, Pak, Ellenberg, and this guy is to prove this exponentially good upper bound for the size of a cap set. So for some constant c, if a set A has more than c times this many elements, it must contain a 3-term arithmetic progression. So this is the big deal. And I'm going to sketch a proof of this, and because this is what has led to this later work that of Kazhdan and Moshkovitz and others. So it's somehow to get an upper bound, an exponentially non-trivial upper bound for the size of a cap set. So Krut, Lev, Pak, Ellenberg, Jesuit, they used what is called the polynomial method. And in one of his beautiful blog posts, Terry Tao gave his sort of variant of their proof. And that's what I want to talk about. So, yeah, so this should have been, I don't know what happened here. So, okay. So lines in a vector space. So this is what I call the toy problem. And I apologize, these slides somehow got out of order. So the problem is to find a set that doesn't contain a 3-term arithmetic progression. There's also something called the Kakeya problem. The Kakeya problem is to see how small a set you can find that contains a line in every direction. And whether you're in Rn, or maybe in Rn, you just want a line of length 1, a unit line segment in every direction, or whether you're in a finite vector space where you still want to have a line in every direction for the Kakeya problem. So now in F3, but this is the finite field with 3 elements. So the toy problem, that is, the real problem is for the positive integers. The toy problem is to see whether you can get a solution in what should be a simpler case, which is a finite dimensional vector space over a finite field. So in a vector space over a field, a line is just something of the form A plus TB, where A and B are vectors and B is not 0. Now in F3, the field only contains 3 numbers, 0, 1, and 2. So a line in a vector space over F3 is a set of the form A plus B, and A plus 2B. That's all there is. So over F3, a line is the same as a 3-term arithmetic progression. And
I'm not sure though, is there a relationship between the Kakeya problem and the capset problem? The capset problem, you're forbidding something. In the Kakeya problem, you're insisting on something. They seem to be sort of...
So they are completely different problems, except for this connection. So the finite field Kakeya problem was solved using the so-called polynomial method. And people, for whatever reason, said, oh, if you can solve the Kakeya problem over a finite field using the polynomial method, you should be able to solve the capset problem over a finite field using the polynomial method. And for several years, people looked unsuccessfully for a way to do this. And then Krut, Lev, and Pak were able, in fact, to use the polynomial method argument to more or less solve the capstone problem over a field with 4 elements. And then Ellenberg and Jesuit very quickly modified their argument to let it apply to the field with 3 elements, which was, for whatever reason, the case that people were more interested in. So the only connection between the 2 problems is that they both involved a combinatorial sort of geometrical type problem over a finite field. The polynomial method solved one, and now it turns out it solves the other. But the problems themselves, I don't see any obvious duality between them. So Terry Tao gave a beautiful variant, if you like, of the original proof of an upper bound for the capset problem. And he did this by just symmetrizing the definition of a capset. And he also used the notion of what is called the slice rank of a D-tensor. So a D-tensor is just a function. You take a finite product of non-empty finite sets, and you look at a function from this into a field. So that's a D-dimensional tensor. That's all it is. So a vector is a one tensor. A matrix, because a one tensor, a vector, you can think of it as a map, like an n-dimensional vector. It's a map from the integers from 1 to n into the field. A matrix, you have two finite sets. One has m elements, the other has n elements. And every pair ij goes to some field element c sub ij. That's a matrix. So a matrix is just a two tensor. And every matrix has a rank. Now, one might like to extend the notion of rank from two tensors, which are matrices, to d-dimensional tensors for any d. And it turns out there are many ways to extend the notion of rank from a two tensor to a d tensor. The extensions are all different. They all reduce to the classical rank for a matrix. And many of these extensions they're not just silly, they're extremely useful in their own right. So slice rank is one of many extensions of matrix rank to D tensors. There's something called tensor rank. There's something called partition rank. There's something called geometric rank. There's something called analytic rank. And it's the equivalence of geometric and analytic ranks that I suspect Moskowitz will talk about in a couple of weeks. In any case, I'll explain some of this and run out of time. Hopefully I'll run out of time before I run out of what I figured out in the past week about all this. So let me just say something about slice rank. So forget everything. Just take a function of n variables, T1 up to Tn. We say it has slice rank 1 if there exist two functions, a function of one variable, T sub I, and a function of the other n-1 variables, V, such that W factors into U times V. So if a function of n variables can be factored in this way, we say it has slice rank 1. And for an arbitrary function, the slice rank is defined to be the smallest number r such that this function can be expressed as the sum of r rank 1 functions. Okay, so that's the definition of slice rank for a function. Okay. Oh, exercise. Prove that if you take T1 plus T2, it has slice rank 2 and not slice rank 1. That just sort of like helps you fix the concept a little bit. Symmetrization. Okay, so we're working in the field with 3 elements. Suppose you have a 3-term arithmetic progression. In the vector space, this is the n-dimensional vector space over F3. B is different from 0. So if you let x be equal to the vector a, y the vector a plus b, and z the vector a plus 2b, these are distinct vectors because b is different from 0. And if you add them, you get this, which is 3a plus 3b, which is 0. So in the field with 3 elements, the sum of the 3 terms of an arithmetic progression is 0. On the other hand, suppose you have 3 distinct vectors whose sum is 0. If you let a be equal to x, b equal to y minus x, and c equal to z minus x, b is different from 0 because x is different from y, and x plus y plus z, that's a plus b plus a plus c, that's 3a plus b plus c, but 3a is 0, and the sum is 0. So b plus c is 0. So c is minus b, which is 2b, which means x is equal to a, y is equal to a plus b, z is x plus c, which is a plus c, which is a plus 2b. So if you have three distinct vectors that sum to 0, they are in fact 3 vectors in a 3-term arithmetic progression. So another way to, this is really not a theorem, but it just condenses what I just said. A set A is a cap set in F3n if and only if A contains no triple of distinct elements that sum to 0. So that's a symmetric definition of CAPSET, because the three components, X, Y, and Z, are treated the same way. It's not like, yeah, okay. Now, let's just define the general delta function. You have some set omega and a fixed point omega naught and omega, and F's a field. So you have this function delta to 0, 1, defined in the delta function way. Delta omega 0 of omega is 1 if omega is omega 0 and 0 otherwise. So that's the usual delta function. And now, let's go back. Here we have F3n, that's the n-dimensional vector space over the field F3. So I'm looking at triples of vectors. And I define two functions to 0, 1, G and H. So G of three vectors, X, Y, and Z, is for every A in, so fix some set A. All right, sorry. A is some subset of F3 of n. Fix some set A. So this is the, for every A, this is delta XA, delta YA, delta, and this should be a Z, delta ZA. And that H of X, Y, Z be delta 0 of X plus Y plus Z. So what this means is G of X, Y, Z, that's equal to, sorry, G of X, Y, Z equals 1 if and only if X and Y and Z are the same. Right? Because if X, Y, and Z are all equal to the same A, there's exactly one term here which is equal to 1. And there's only one term which is equal to 1. And if some X is different from Y, then every one of these terms is 0. So this function G equals 1 if and only if X equals Y equals Z. And H of X, Y, Z, that's this delta function, X plus Y plus Z 0. This is equal to 1. Again, this should be a 1, I'm sorry. If and only if X plus Y plus Z equals 0, right? So
yeah, of course, H can't tell if you're looking at a 3-term progression or at the same vector 3 times.
Correct. Yes. So this equals 1 precisely when these sum to 0. This equals 1 precisely when they're the same. So this statement that A is a cap set means that there's no triple of distinct elements to satisfy this. Equivalently, the set that A be a subset of the vector space, the set A is a cap set in F, 3n, if and only if G of X, Y, Z equals H of X, Y, Z for all triples of vectors in A, okay? So this function equals this function, G equals H, if and only if A is a cap set. So again, A is a subset of the vector space. Now I haven't really said very carefully what slice rank is in different situations, but associated to every function from A3 to F3. So this is a function of 3 vectors, or if you like, a function of 9 variables. There's some slice rank associated to this function. And
why 9 variables?
Well, because X, Y, and Z are 3-dimensional vectors. So
they're not 3-dimensional, they're n-dimensional.
I'm sorry. They're 3n. Thank you.
That's it.
Yeah.
Mel, I'm a little bit confused. There are 2 ones that you introduced, one in characteristic 3 and one in characteristic 0. So
no, I'm only working in characteristic 3.
Okay, that clears it. Thank you.
The G and the H are taking values in the original field, F3.
Everything is in F3. I will say when I look at Terry Tao's paper and all of this is sloughed over, but it only makes sense if everything is in a fixed field and the field is F3. So,
okay.
Yes. So this is a function. If you like, it's a tensor. It has a slice rank. And I'm not going to prove it today. If there's no speaker for next week, I'll go back and try and prove some of this stuff. But this function actually has slice rank, which is the cardinality of the set A. Okay. So this function G has cardinality A. What about the function H? The function H has a slice rank, and I can find an upper bound for it. Somehow, the upper bound for this function is constant times 2.756 to the power n. Okay? I'll show you in a moment how you get this kind of ridiculous statement. But if A is a cap set, then G equals H. The two functions are equal. So the ranks are equal. But G, if you believe any of this, and there's absolutely no reason why you should, if you believe any of this, G has rank cardinality of A, and H has rank no bigger than this, and rank G equals rank H implies that the cardinality of a cap set is bounded above by this exponential function, which is a lot better than 3 to the n. Okay? So this proof of the cap set theorem is reduced to a calculation of the ranks of two functions. All right? Again, I do not suggest anyone believe anything I'm saying, but because I haven't justified any of it. Anyway, but this is the idea of Turry-Tau's proof, right? So let's see. Let's look at the function h of x, y, z. So let's just recall a simple fact. Everything is in F3. In F3, T is equal, so T is an element in the field. T is 0 if and only if 1 minus T squared is 1, right? Because if T is 0, this is 1. If T is 1, this is 0. If T is 2, this is 0. Sorry, yeah. So this is 1 if and only if T is 0. Right? So take three vectors, x, y, and z, all in F3. So
yeah, sorry, but I must point out that that statement had nothing to do with F3.
Excuse me?
That statement has nothing to do with F3.
Well, if you're in F5, it's not true.
I must be missing something. Cancel the ones from both sides. You get minus T squared equals 0. That'll mean that T is equal to 0. You're working in a field.
Wait. So I hope I'm not screwing something up because I had zeros where I should have had ones before. But you're correct. This is always true.
This is just field arguments, no particular field.
You're right.
Involved.
No. You are 100% correct. Okay. Take three vectors, x, y, and z. So the sum of the vectors is 0, means this vector equals this, which means each of the coordinates is 0, which means 1 minus the sum of the coordinates squared is 1, right? Because this is 0. And
in the passage from this line to the next line, you use the fact that you're in F3.
Okay.
When you're taking the product, if you'd been working in a different field, you could have a product of things which are not 0 or 1 end up being equal to 1. But in F3, you have a product equal to 1. This thing is going to be 1 or 0. So the only option, yes, fine. Yes. This is where you're using F3 here.
Okay. So this is 1 if and only if each factor is 1. And because each factor is either 0 or 1. So x plus y plus z is the 0 vector if and only if this product is 1. So let's see. So if I take the function h of x, y, z, which is this delta function, it's 0 when x plus y, it's 1 when x plus y plus z is 0, and 0 everywhere else, this equals this. So this function can be represented in terms of the coordinates of the vectors like this. And this is a polynomial of degree 2n in the 3n variables x1 to xn, y1 to yn, z1 up to zn. Each of these factors is quadratic, which is why the total degree is 2n. And h itself, when you multiply this out, it's a sum of monomials. So each monomial is a product of x's, y's, and z's to various exponents. The total degree is at most 2n for any one of these monomials. The exponents are either 0, 1, or 2, because there's no variable which appears with degree greater than 2. So just to use standard notation for monomials and several variables, if you take an n tuple in 0, 1, 2 to the n, these now just integers, x to this n tuple I is x1 to the I1 up to xn to the in, and the degree of this monomial, or absolute value of I, is just the sum of the coordinates of I. So every monomial in this expression, when you multiply this out, every monomial in this polynomial has a degree which is size of I, or not size, it's whatever you want to call it, absolute value of I absolute value of I, absolute value of j plus absolute value of k. This is the total degree of this monomial, and it's in most 2n. So, okay, it's in most 2n, which means they can't all be bigger than 2n over 3. So at least one of these three integers is less than or equal to 2n over 3. So this function h of x, y, z, which is this polynomial, I can write it as follows. So I, j, and k, in every one of these terms, at least one of these exponent vectors has total degree at most 2n over 3. So I can choose all of the i's for which the weight of I is at most 2n over 3. And so I can pull out from this all the terms where I is less than or equal to 2n over 3 times the sum of monomials in y over z, and y and z. So that gives me this first expression. Now, I look at everything that's left, not everything, but just everything that's left. And in everything that's left, the weight of I is bigger than 2n over 3, but either j or k has weight less than or equal to 2n over 3. So I pick out all the monomials in y with weight no greater than 2n over 3, and I can write some of these remaining terms as y to each of these j times the sum of monomials in x and z. And whatever I haven't used yet, I and j are both bigger than 2n over 3, but k is weight less than 2n over 3. So I can write everything that's left in this form. So that's the way to interpret this expression. It doesn't mean all terms j that satisfies this. It's all terms that haven't been used here, and here it's all terms z to the k that haven't been used previously. But I can write h in this way. And now you look at this and you see this is...
I do have to interrupt once more. Obviously, at this point, the i's are not in F3 anymore. They're ordinary integers.
No. I said the exponent vectors are integers.
Right, yes.
Yes. I mean, these are polynomials, but they're polynomials, but the exponent vectors are integers. So, and if you look, each of these is a rank 1 function the way I defined slant rank previously. In terms of x, y, and z, this is something in x times something in y and z. This is something in y times something in x and z. This is
You mean each one of the individual terms in the summand? You don't mean the
each
whole
one,
sum of the coordinates.
each one of these terms individually is rank 1 in the vectors x, y, and z. And I want to count how many terms there are altogether. So for example, I want to count how many n-tuples of I1 up to In, where these numbers, these are integers, 0, 1, or 2, with the condition that their sum is no bigger than 2n over 3. So in each such n-tuple, these numbers are 0, 1, or 2, so that m0 be the number of these coordinates equal to 0, m1 the number equal to 1, m2 the number equal to 2. So m0 plus m1 plus m2 is n, and the sum of these numbers is no bigger than 2n over 3. So this really means 0 times m0 plus 1 times m1 plus 2 times m2. That's the weight of I, which is just m1 plus 2m2. That's no bigger than 2n over 3. So for each such triple, how many monomials are there? Well, it's exactly the trinomial coefficient n choose m0, m1, m2, right? Given the n variables, this is the number of ways you can choose. You can partition them into 3 sets with cardinalities m0, m1, m2. Those in the first set get weight 0, in the second set get weight 1, or degree 1 in the third set. In this set get weight 2. So the total number of monomials x to the I, which satisfy this constraint, is for every triple that satisfies these numbers, there are this trinomial many such monomials. So the number of terms here in this first set is at most this number, which I call capital N. And in each of the other sets, you have the same count. The number of J's is at most capital N. The number of K's is at most capital N. So the number of the number of functions here, or if you like, the number of rank 1 functions on the right-hand side is at most 3 times N.
Although it seems like you might be able to improve something, because in that sum, the things where the y coordinates were less than 2/3 n, it's the things that are left over. So it might be that there's somehow fewer of them. You might be able to improve the bound somehow.
Yeah, it might be. I don't know.
But probably you wouldn't change the exponent any. So what's the point?
Well, yeah. So how do I count this? I mean, this is some trinomial coefficient. I want a number for it, right? That's the whole point. I want a number for it. So, so for people who actually know calculus, or Terry Tao has wrote a whole blog on calculating this. If you take your standard entropy function, so you take alpha, beta, gamma, non-negative real numbers that sum to 1, the entropy of alpha, beta, gamma is alpha log 1 over alpha plus beta log 1 over beta plus gamma log 1 over gamma. And I want to compute the entropy of that. I want to find the maximum value of this function subject to the constraint that beta plus 2 gamma is at most 2/3. So you can use Lagrange multipliers. Now, I have to confess, life being short and the talk being imminent, instead of taking a big piece of paper and spending 2 or 3 hours making one mistake after another, I just went to Maple and I opened Lagrange multipliers. I put in the problem, and this is what it gave me for alpha, beta, and gamma. And not surprisingly, it's exactly what Terry Tao also put in his blog. I will say probably Terry is better at doing calculus than I, and maybe he actually calculated it. But in any case, I trust both Terry and Maple when they agree. So you get alpha, beta, and gamma. And then there's some general theory nonsense about So this is the alpha, beta, gamma that maximizes the entropy. So when you compute X to be this number, it just turns out to be 1.01345. And the size of the trinomial coefficient is e to the n capital X plus little o of 1. You get 2.756 to the n. So this is, with a grain of salt, if you like, how one calculates the slice rank of this function h. To calculate the slice rank of the function g is much easier, but I stopped writing slides a few minutes before I logged on to
Could you back up a slide, please? Oh, I see what's this h and the h you did in the next slide with the entropy. They're not the.
I meant to use the lowercase h here.
Yeah, they're not the same. I mean, there's
the
entropy function.
This is lowercase h for entropy. That should have been a lowercase h.
Okay.
Right. This is the entropy function.
Yeah, I mean, without going into too many details, what's happening is that you could think of it as, I mean, like if you were taking a normal distribution and you were cutting off, let's say the, I don't know, the lower third of it, then you'd be looking at a very small tail of the distribution. And that's exponentially small. That's what we're doing here.
Yes.
I mean, it's in two variables instead of one, but yeah.
Yeah. And as I say, in the email I just sent out, maybe last night or this morning, I actually included both an article by Terry Tao, the article by Terry Tao in which he does this, and also a very recent article, just a few months older, from Tim Gowers, where he calculates the slice rank of the sum of some D tensors. But in Terry's blog, there's a link to his previous blog entry, which is devoted completely to proving this. That is this estimate for the trinomials. Okay. Okay. Now I want to. So, if you like, this is a sketch of Tao's variant of the proof of the CAPSET problem. Right. It reduces the problem to showing. It shows that the problem is equivalent to one function being equal to some other function, which is a polynomial. So those two functions have the same slice rank. One of them has slice rank exactly equal to the cardinality of the CAPSET A, and the other has slice rank bounded above by this 2 point something to the power n. Okay. Now, I just want to give you some idea of how slice rank of a tensor reduces to the rank of a matrix that you learn in preschool or somewhere along the way. So now we're back in the world of linear algebra, and we have an m by n matrix. So I apologize if this seems too simple, but I'm actually still trying to figure it out myself. So you have an m by n matrix with coordinates in some field f, your favorite field. And you look at the jth column vector of the matrix, and the rank of the matrix is the dimension of the vector space spanned by the column vectors. So a matrix has rank 1. What does that mean? It means the vector space spanned by the column vectors is one-dimensional. So every column vector must be a scalar multiple of some single non-zero vector. So there's some vector A and non-zero vector, and the jth column of the matrix C is the vector A times some scalar B sub j. So this is what the jth column looks like. And if I write B as a vector, it's going to be an n-dimensional vector because the matrix has n columns. It has to be a non-zero vector. Otherwise, this is the zero matrix and the rank would be 0. So we have non-zero vectors A and B where the ijth coordinate of C is AI times Bj, which means the matrix C you can write as the product of this column vector A times the transpose of the column vector B. Right? So every rank 1 matrix looks like that. Now, let's go from matrices to bilinear forms. So if you have this matrix C, it defines the bilinear form phi C as follows. It's just, this is just, again, it's the chapter 1 of linear algebra. It's X transpose C times Y. It's this bilinear form. And if C has rank 1, then this coefficient Cij is AI times Bj. So your bilinear form looks like this, which factors. So this is really a product of 2 linear forms, a linear form f of x and a linear form g of y. So f of x is this summation ai xi and g of y is summation bj yj. In fact, they're non-zero forms because the vectors a and b are non-zero. So every rank 1 matrix gives rise to a bilinear form, which in the rough sense I define slant rank. This is slant rank 1. This is a slant rank 1 function. Suppose you have a bilinear form of rank R.
I think you may have been saying the wrong word just a second ago. You said slant rank.
Right.
Slice rank. Slice.
Oh, sorry, slice rank. Thank you. Yes.
Yeah. Okay. I mean, is there a slant rank, or was that just a mistake?
That's just a mistake.
Okay.
So bilinear forms have rank R. So if your matrix has rank R, this means there are linearly independent vectors such that each column of the matrix is a linear combination of those R vectors. So that means, if you like, the jth column of your matrix is some linear combination of these R vectors. So the ijth coordinate is this. So AK, for K going from 1 up to R, AK is this m-dimensional vector, and Bj is this R-dimensional vector. There are RKs and there are NJs, right? Because they're N columns. So if I define the linear forms, for each of these vectors AK, I have a linear form. For each of the vectors BK, the subscripts are slightly messed up, but certainly for each of these vectors, I have a linear form. So the linear form that comes from the matrix C, X transpose C times Y, this is the linear form, but each Cij is a sum over K of X Aik Bkj. And you rearrange this, and what you get in the end is the bilinear. If C has rank R, then the bilinear form phi C is a sum of R products of linear forms. Each of these is a slice rank 1 function. So the slice rank of phi C is at most, of the bilinear form, is at most R. And conversely, if this function, if the bilinear form, it can be written as a sum of R products of linear forms, then each column of the matrix is a linear combination of R vectors coming from the FKs. And so the rank is at most C. So the baby theorem in linear algebra from this is that the rank, this is the ordinary vector space rank of an m by n matrix, is the slice rank of the bilinear form associated with the matrix, which means it's the smallest number R, such that you can represent this linear form as a sum of R products of linear forms in X and Y. So this is just to indicate a kind of connection between slice rank in dimension 2 and vector space rank. Whew, okay. So that is a rough sketch of Terry Tao's proof. Again, in my email to everyone, and if you didn't get it, I'm happy to send it to you. I included Terry Tao's blog post and also Tim Cower's very recent contribution to calculating the slice rank of a function. And that's what I want to say. Yeah. So unless I can find a speaker for next week, hopefully I can, but I think it's 3 weeks. So today's the 18th. Wow. Oh, so next Thursday is Thanksgiving. We have no seminar. Then we have the first Thursday in December. And when is Guy Moskowitz speaking? He's giving the last seminar of the semester, which is on Thursday, December 16th. So on the 2nd and the 9th, we have seminars. And I would be particularly happy if someone wants to figure out and can explain geometric rank and analytic rank. I will say for myself, I finally figured out something I could never understand. I mean, I learned vectors, I learned about tensor products. You know, it's a universal object in some category. You have multilinear maps, they factor uniquely through a tensor product. They're beautiful theorems about tensor products. And then you see a physicist who talks about tensors as something with lots of subscripts and superscripts. And I could never figure out what these guys were talking about. And until I started to look at this stuff last week. And then I realized they're not talking about anything. They're just talking about things with subscripts and that maybe transform in some way. So you just have to take one of the physicist's tensor products and think of it as the coordinates of a tensor product with respect to bases for, let's say there's over vector spaces or free modules, and it transforms the way it's supposed to transform. But I swear I couldn't, whenever I saw a physicist's paper writing a tensor, I would look at it for a few minutes and just decide it was incomprehensible and go on to something else. So yeah. And for those of you who might remember from a couple of years ago, when I was talking a lot about Sinkhorn's methods for transforming a matrix into a doubly stochastic matrix, there's a whole large literature on extending Sinkhorn's method, if you like, to tensors, right? So the matrix is a 2 tensor. And what happens if you do something analogous to try to get something like a multiply stochastic D-tensor? And there is a very interesting literature on this subject, which if I live long enough, I might have a chance to look at. But it really is very interesting. And I will say in their paper on their important paper that got a lot of write-up in Quantum Magazine, Alex Cohen and Guy Moskowitz actually refer to some of Sinkhorn's work and what they do. So on the principle that everything is, so this reaffirms the principle that everything is connected to everything else. Okay, well,
all right.
Stop
Okay.
share.
Thanks very much.
Okay.
By the way, December 16th is the West Coast number theory.
Is it actually meeting in person?
All they've promised is that there's going to be a meeting, and they don't know how.